So I'm Yoav from Wix, and what we're going to talk about, CAP Theorem, is probably one of the most important theorems for us when you work on internet companies and on scaling out, scaling systems, any kind of distributed system. One of the things that people associate CAP Theorem is with databases, which is true, but it's not correct by itself. CAP Theorem is about any distributed system, regardless of whether that system is a system to store data or to do any kind of other functionality. And understanding it is kind of key in order to build resilient distributed systems. So Wix, where I come from, we are creating stunning websites. Basically, it's a do-it-yourself tool to build websites. Very easy to build stuff. You have an online IDE, online editor, where you can just drag and drop stuff. You can take pictures, you can take text, you can take videos, just drag them on the screen, click on a publish button, and you have a website. Over 60 million websites to date. We have also tools to manage the back office of the business owner, and we launched CRM systems for our customers something like a year ago. It already has about 80 million people in it, and we have a growth of over 1 million new sites a day. I can just, maybe it'll be easier to take it. All right, sure. Second, we have a growth of over 1 million new sites a day. But that's not what I came to talk about. To talk about CAP Theorem. So CAP Theorem was set by a guy named Brewer in about 2002. And it's not really a theorem because it doesn't have a mathematical proof, but it is considered as a theorem for us, or effectively a theorem. It basically means that for any distributed computer system, you cannot provide simultaneously those three guarantees. Consistency, which basically means that all of your nodes see the same data. Availability means that when you send a request to that system, you'll actually get a response. And partition tolerance means that even when you have any kind of either message loss or failure or something goes wrong in the system, whether that system can actually cope with that condition. So Brewer, by the way, is working for Google today and is I think in the Google Cloud team, working on their data stores. But they kind of don't know, I haven't really met him, so I don't really know what he's doing there. Anyway, what all this stuff means in practical terms is that for anything that you're doing, which is internet scale, you need to drop data consistency. It's not practical to have data consistency on anything which is internet scale. If you want availability, you want your customers to get a service with those 5, 6, 7 nines, you won't have data consistency. Sorry. So let's go for a simple example. Let's say you want to buy a book, Tales of the CAP Theorem. And there is only one book in the stock. So there's only one in the inventory. So kind of means that only one person would get that book, probably. So as you browse and add that book to your shopping cart, someone else goes into the shop and tries to buy that same book. If you're talking about a consistent environment, consistent system, so a service is consistent if it writes fully or not at all. So there's no in-between states. There's only one copy of the book and only one person will get it. If both customers actually manage to buy the book, that lack of consistency will be a problem, because just think about it. We took money from 2 different people. Only one of them can get actually the merchandise. One of them would probably be unhappy. Scale that problem for many people and not just one person, and you get a problem. If that happens with, let's say, 0.1% in the scale of a company like Amazon, the books seller Amazon, that will drive them down. So that's something that we don't really want to have when we are selling products. And consistency in CAP Theorem is what we called A, or in the ACID. Anyone who knows what ACID is? You heard the term? There's one person there saying kind of. So ACID is basically the guarantees that SQL databases talk about all the time. And one of those guarantees, atomicity, basically says that any transaction is all or nothing. That's what the transactions in SQL databases. And cap theorem consistency is kind of like the same guarantee. There is one difference where in SQL databases, they are talking about consistency of the whole database. So all the state, all of your tables, everything has to be consistent all the time with SQL databases. In cap theorem, they actually limit it to a per operation or per what you're doing right now. But it's the same idea. When talking about availability means basically the service be available. So you purchase a book and you clicked on the purchase button. So you enter your credit card, you entered all of your details, shipment, and so on. You clicked on buy. You expect to get a response. Now, if you get a response saying, thank you, you just purchased the book, you'll probably be happy. If you get a response, we're sorry, someone has got the last book before you, you might be a little bit sad, but you'll know where you are at. If you get a response, what would you think just happened? That's what availability is about. To actually get a response, it might be a failure response, might be a bad response, but at least get something back. And the problem with availability is that when you need it, it won't be there. And the other thing about availability is that it doesn't really matter if your server or your application is up or not. What does matter is whether your client or the people using your system can actually reach it and can get a response and can get a response in the time they expect to get a response. So if you actually get that person a response a few days later that, oh yeah, you got your book. You might have went and bought that book somewhere else by the time. And then you might be really unhappy. Partition tolerance, and that's the last part about the terms in that cap theorem, it basically means what happens when your system or parts of your system, remember, we're talking about this distributed system. It's not just one node, it's a few nodes. What happens when they can't communicate? And servers not being able to communicate is equivalent to a server crash or a node crash. If you're trying to contact someone else and it doesn't respond, you don't really know if it's there or not, or there's a problem, there isn't a problem. You just know you can't talk to it. The only solution to solve partition tolerance and being resilient to partition tolerance is to run on one system, on one node, and not have a distributed system. But once you actually want to scale, and just one host has its limitations. You all know that. You can't scale up infinitely. So at some point you have to scale out, which means you're going to need to cope with partition tolerance. And a lot of people say, so partitions, are they real? Does it really happen? Does we really get problems that nodes don't communicate? Our network is reliable. We're doing networks for 40 years. We use an IP, which is basically designed to be resilient against atomic attacks. So how can that be that we can't really guarantee that messages are passing between one server and another? And that's exactly the point. In an IP network, by design, the IP network is allowed to drop messages between two hosts. It allows to delay messages. It allowed to duplicate messages and deliver them more than once. And it is allowed to reorder messages. And all of that is in order to get a resilient system. But it's not consistent by design. It's resilient. Which means that for us, things like delays are exactly like drops. It means that in the real world, when you look at different cases, I know the text is a bit small, but believe me, there's a lot here. There are published examples from Netflix, Twilio, Fog Creek, AWS, GitHub, of course from us Wix. Microsoft has published that on average they have a failure rate of 5.2 devices per day and 40.8 links per day. They have a median loss of about 60,000 packets a day, IP packets. Even with network redundancy, it only improves that by 43%. So there's a big a big chunk, big number of failures that happen there. A lot of companies that face stuff like that. Why is that happening? GC pauses are basically a delay, and those can be rather long in some cases. Network maintenance, seg faults, crashes, faulty network interfaces, bridge loops, VLAN problems, all kinds of hosted networks. The cloud, by the way, is a major contributor to those problems, because on a cloud, you're guaranteed to not have a guaranteed network, and you're guaranteed to not have guaranteed resources. So you're guaranteed to have random delays. And there's all kinds of other stuff. You can have, I have a link that if you want to follow up, you can get an article which is about, I don't know, something like 10 pages long of just summaries of failure cases like that. So partitions are real. They're a real problem. And we need to cope with them. So I'll try just to explain why is that. How is that all that stuff happening? Just to give you a proof, but I'm not going to go into mathematics because I don't know if before lunch that's the real time to go into mathematics. And by the way, that was really proven mathematically. So I'll take a simple example. Let's say we have just two machines, two hosts. We have one host and one that runs a process A that wants to write data. We have another machine that runs a process B that wants to read data. And we have some process that replicates the data from the first database to the second. And in the sunny day scenario, we write the data to our database. It is replicated and we read the data. Everything works fine. What happens if the messages from one host to another to the second can't move, can't reach the second one? If either we're losing them or they're delayed. At that point, we might write some value on the first host, but the second host will read the old values. And actually, the guy on the first host, the guy who wrote the data, because he doesn't wait for the replication, he's not even aware that, you know, A wrote some data, he got an acknowledgement, everything is fine, your data was written. But when B reads the data, he gets stale data. So we don't have a consistent system at that point. What we can do, we can have a wait for that replication and make basically the replication synchronous. We can do that. What will happen in that case? A would try to write the data. It will succeed actually in writing the data, but at that point it will wait for the data to be replicated into the second host. Because we can deliver messages, that replication doesn't work, we'll have to fail the write on A, because otherwise A wrote data and didn't replicate. So actually we've lost availability. And this is an example with just two hosts, and a very simplistic example, but that is actually why you have to trade between availability and consistency. Do you wait to get an acknowledgement or do you not? That's in a very simplistic way what happens with the CAP theorem. So what do we do about it? Because at the end we're not really interested in mathematics, we're interested about doing real stuff in the real world. So the practical terms mean that in any distributed system where in any distributed system that wants to be resilient for partition tolerance, basically we have to be resilient for partition tolerance because a network that doesn't drop messages doesn't exist, and nodes that don't crash don't exist. So we need to have partition tolerance in whatever solution we're doing, which means we have to make a choice. Consistency over availability, or availability over consistency, or neither, which is also a valid choice. And just to give you something which is really help in understanding what it means or how to cope with it, is the fact that CAP theorem is local. And when I say local, I mean it's local for an operation. So you could have in one system, you don't need to choose all of which is going to be consistent and not available. It doesn't work that way. What you can do, you can select per operation what you want to do. For instance, in the shopping cart or in the e-commerce example, you can select that the checkout process will be consistent, but the add item to cart process would be available, highly available. And that's actually the choice that Amazon have done. You can, as you browse the shop in Amazon and add and remove products from the shopping cart, you can see different states of the shopping cart at the same time. But once you click on the checkout button, you'll get a consistent shopping cart. And so let's try and see how different tools stand against CAP Theorem. What's going on in the real world? There is a nice guy called Kyle Kinsbury. He has a blog called afear.com, and he is, I guess, doesn't really have a life, or he has a very interesting life, depends how you look at it. But what he's done in his weekends is installing different databases on 5 hosts and running a benchmark on those databases, and then cutting off the network and restoring the network, and then measuring what happened to those databases. What did this network failure cause to the data they have in the database? Of course, there was some data that wasn't written or couldn't be read, because that's expected. But did we preserve consistency? Did the data, or what way the nodes got through in that process, was actually what they expected to happen, or what the database told them at that point? Was it real, or did it done strange stuff? So let's take a very simple example, Postgres. So Postgres is an SQL engine. It's a consistent environment, consistent system. We're actually thinking about not a CP, it's a CA, because it's a single node, and it's highly available, or considered to be highly available, considered to be consistent, and it accepts writes only on a single primary node and ensures that writes are written to slaves as well as you write. In that regard, the Martian slaves are a CP system. If a partition occurs, we cannot talk to the server and the system is unavailable. And we should be consistent. But the distributed system that is composed by the server and the client in Postgres, it might not be consistent. And to be honest, that's true for any SQL engine. And what it means is that they might not agree on if a transaction actually took place. Sounds strange, right? Let's see how that happens. So the way that a commit happens in Postgres is in the 2PC protocol. It basically means that the client votes to commit, sends a message to the server, to Postgres, please commit the transaction. The server does all of his magic, all of his checks, writes the transaction to storage, basically commits the transaction, and returns an acknowledgement to the client. And then the client knows, yeah, the transaction was committed. At that point, the server could have said something like, we have duplicate key, send a message to the client, transaction rejected, and the client will have to cope with that. What happens if that acknowledgement doesn't arrive to the client? So, at that point, the server, Postgres, actually wrote the transaction, so it was committed. But the client will wait and wait and wait, and at some point we'll probably get some kind of network error. So does the client know if that worked or not? It might be a network error as it tries to write data, then the data actually didn't arrive, the commit actually didn't arrive to the server, or might it be a network error after the transaction was posted on the acknowledgement as it gets back to it? So an experiment that was done, it took 5 clients who tried to route to a single Postgres and dropped the network at some point. Out of 1,000 writes, 950 succeeded. 48 failed, which is fine. We have a failure, we have success, that's fine. But we had 2 writes that were false negatives. The client got an error, actually a timeout error, but those transactions were actually written. And that case can actually happen with almost any kind of SQL database. So we could accept those false negatives, that's fine. We can say, if we get a timeout, a read timeout exception, or read timeout failure when you work on an SQL data engine, we can say, yeah, that's fine. The transaction was probably written. Another thing to do is to use idempotent operations. on network error, just retry. And you can use something like a transaction ID, just add another table, have the unique ID, have the client generate some kind of a value that inserts into that table. The transaction can't be committed twice trying to insert the same value to that table. That already makes that transaction, to some degree, unique, if not idempotent. So that's a very simple strategy. Let's go for more interesting cases. MongoDB. How many people have tried MongoDB? Quite a few. So how do you think MongoDB is a good tool or a bad tool? Depends for what is a very good answer. So the way that MongoDB does replication is using replica sets. You write to one node and then it replicates to all the others. To some degree that sounds kind of similar to what Postgres is doing, except that MongoDB selects automatically who is the leader, who is the master. And how is doing that? There is some protocol where they select a semi-random, semi-based on some other parameters to figure out which one of those 5 nodes is best to be the leader at a certain point. But unlike other systems, or unlike SQL systems, MongoDB may revert operations in some cases, and we'll see how that happens. So in case of partitioning, where our network is split between, let's say we have 5 nodes, 5 Mongo nodes and 5 clients, and at some point we have a split where we have 3 nodes and 2 other nodes. How can something like that happen? Let's assume we have 2 zones, and we have 3 nodes in one zone and 2 nodes in another zone, and connectivity between the zones fails. Or we have two data centers and we have some problem like that. Or might be even a failure of a link between 2 racks. A lot of stuff might happen. The group that is the majority, the tree in this case, will select a new leader based on the highest uptime. Uptime is basically one of the nodes who think it's the most updated. The primary, if it's part of the 2, the minority, will be demoted to secondary and will stop accepting writes. So that sounds, that's the way it should happen. And then our system continues to work with the new leader. We can still write information. When we fix the problem, all the nodes would sync, and we have our system back, and everything looks cool and consistent. Is it? So let's have 5 hosts, 5 clients, partition the network, restore the network, and see what happened. So in MongoDB, there is something called the write concern. It basically means when I write data into MongoDB, as a client, what guarantee I want to have that my data was written. Now, the default used to be something like a year and a half ago, 2 years ago, unacknowledged. Basically means the client sends information to MongoDB. It doesn't even wait to get to hear what happened with the data. So that was the first try. 6,000 writes, 5,700 actually got acknowledged. Only 3,300 survived. And basically means we had 42% data loss that was acknowledged. 42% of the writes that we think, as the client thinks were successful, were lost. How did something like that happen? So the problem is that there is a time gap between the time that we have network partition and the point in time where the primary understands is part of the minority. And during that gap, it still accepts writes. So at that point, we have actually two primaries that accept writes. We have one majority that accepts writes. In the majority, we have a new node that accepts writes. In the minority, we have a node that accepted writes up to a certain point. And when we restore the system, now we have conflicting writes. Now, Mongo uses a single counter to know, they call it the uptime, to know how many writes were done. So what Mongo is going to do is going to find of those 2 nodes, those 2 primaries, the one that has higher uptime, and the second one would revert and basically delete all the writes that happened after that point when they have diverged. So by design, at that point, Mongo will delete data. There is actually a feature that this deleted data would be backed up to a log on some file. At the time that this test would run, it did not work. It might work today. But let's go on. See that we've done a test with unacknowledged. Basically, what did we expect when we ran a test with unacknowledged? Let's try using acknowledged write concern. There is a safe and acknowledged write concern. Basically means that you write, the node gets the data and sends a response back to the client. Yeah, I got the data, everything is fine. 37% data loss. It's an improvement, but still 37%. There's another write concern called replica safe or replica acknowledged, meaning that Mongo would actually write the data to at least 2 nodes. Actually, if I remember right, actually that picture is actually wrong. That's from Mongo, because it does write to 2 nodes, but the primary is counted as one of those 2 nodes. And in this case, they actually got 33% of data loss. And simply because of the reason, what if those 2 nodes are not part of the majority? And what if they are, but the selected leader is actually some other node? And the replication to the other slaves, other secondaries is done async. So they might have not gotten the data. So we're improving. We got from 42 to was 37, now 33. Let's try write concern majority. Basically means that as we write to Mongo, it's going to write to the majority of the nodes in the cluster. At that point, we add 6,000 writes, 5,700 acknowledged, 5,701 survivors, 2 acknowledged writes lost, 3 unacknowledged writes found. So the 3 unacknowledged writes found is exactly what we had with Postgres. It's the case of the false negatives. That happens. The 2 acknowledged writes that are lost, that's a problem. But apparently, that problem was a bug in MongoDB, in the replication protocol, and they fixed it since. So today, if you use MongoDB with majority, you'll basically get a consistent system. But you're going to pay in performance, quite a bit. So, takeaways. First of all, we are using MongoDB in Wix. It's a great system. It's a super cool database. What you've seen here is aspects of how to use MongoDB and the trade-offs in a distributed system. We could accept data loss, and remember, it's statistically. It doesn't happen all the time. And here the percentages were really high because in the test, someone actually created and crafted a failure to be gross enough for us to see what happens. Or you could use write concern majority, which is totally fine, with impact on performance and availability, of course. Write concern majority in the case of a network split would lose availability, of course, because we can't find a majority at that point. This guy, Kyle, tested other databases, Redis, React, NowDB, Cassandra, Kafka, Zookeeper, and so many others. React, for instance, the one we heard about, I think 2 or 3 lectures ago. In React, they add, in one configuration, 71% data loss, much worse than MongoDB. In another, 0 data loss, in another configuration. So basically, what I'm trying to say, there's no magic here. Any of those tools, you need to really know what you're doing and how much you care about your data and what you're trading off. And that's a really important point with not only with SQL databases and non-SQL databases, but with any kind of distributed system. How much time do I have? Do you have more time? 5 minutes? Not a lot. Okay. So I'm not going to go into strategies for using data. I'm just going to say a few words about them, because there are quite a few strategies to cope with those limitations or with the real world. There are things like there's what's called base, which is basically trying to have an available system that is not really consistent, it's statistically consistent. And you probably heard about eventual consistency, which are systems that allow a certain amount of inconsistency to exist for a certain period of time and tries to regain consistency as fast as they can. Such systems have always need to cope with conflicts, and they can cope with conflicts by selecting the newest record, basically dropping the old one, assuming that is the right thing to do, or by having a merge function that you need to try and code what happens in such a case. There are the stuff like CRDTs that I think were mentioned earlier, but they are very limited. There's very limited data structures, but they're trying to do stuff that is consistent regardless of the cap theorem. So for instance, there is one data structure, one CRDT data structure, which is a set that you can only add stuff to it. You can't remove anything from that set. It's just a set that you can add stuff into the set. That's one CRDT. Another CRDT is actually a set that you can add elements into and then remove elements from, but you cannot re-add elements to it. And of course, the simplest CRDT is a counter. Other patterns are things like CQRS, which is a command query responsibility segregation that allows you to tune per operation how much consistent or inconsistent you want to be, but they are very drastic stuff. Things like using immutable data helps a lot. Any kind of update operation is actually delete. I don't know if you've noticed that, but an update operation in database is delete operation. It destroys data. And using immutable data makes it much easier because you don't have you can mold your system to actually don't have conflicts if you use immutable data. But you need to change quite a bit of what you're doing. And even if you are using immutable data and you're using existing engines, you need to remember that the existing engines assume your data is mutable and they will destroy it because of good reasons, like MongoDB does or React or other tools does, simply because they don't know what you mean, that you mean your data to be immutable. You need to really think about the patterns of how to do something like that. That's it basically.